In the previous section, we were looking at mapping the data into the genome and then using string dye to get the transcript abundance. This is somewhat slow in big genomes like wheat, and therefore sometimes it is advisable to use k-mer-based quantification of transcript abundance. So this is much, much faster. There's no real mapping, and it compares the reads directly to the genes. So the reference is the coding sequence and not the whole genome. So if you think about the wheat genome, the amount of sequence that's covered by reads, covered by genes is much, much smaller than the whole genome, because you can just ignore all the repeats and transposable elements. And here what happens, you have these 3 exons, and then you don't have to worry about exon intron boundaries because they are just together as CDS already. And how to do this? We have k-mer-based quantification of transcript abundance. And shortly, what is k-mer? So k-mer is a sequence of fragment length k. And for instance, if we have k equals 5, and we have sequences ATGG, TTG, and TTGG, CGC, we get 5 mers. So you chop the first one into first 5 bases, the next 5 bases, and the last 5 bases. So from the first one, you have 5 mers, and from the second one, you have another 5 mers. So these would be the short reads. So you had a sequence of length 8, 7, and you get 5 mers. And then now we assume you have gene, which is slightly longer, but you similarly snip it into fragments of 5. So ATGGT, TGGTT, GGTTG, and so on. So you have all these fragments, and then computationally, you compare these 5 mers together. You forgot all about these reads and all about these genes, and this is really, really much quicker and easier than mapping, and it can be used for RNA Seq quantification. So here we are going to use a program called Callisto to do the quantification. And here the reference is the CDS set, which is much, much smaller than the whole genome. Therefore, it's also much faster. And there's a default k-mer length 31, but this can be changed if needed. There often is no reason to change it. And this is run as normal. So first you do indexing, which creates a binary files that will be studied by the computer. And then we do Callisto quantification with the read data. So let's go to the virtual box again and see what happens. So there's Callisto in the virtual box already. So if you type Callisto, it gives helpful commands, and Callisto index is one of them. Now we are actually in the folder of the data. So let's see, ls, there is the Callisto Cariha version 1 locus CDS FASTA. So this is where our data is, and we should go to the analysis folder to do the analysis. So Callisto index, and then -i, let's go Cariha index. And then we have to go back to the data folder and type this locus CDS FASTA and press enter. Really quickly, it creates the index, and now we can just do the Callisto quant. And let's check the command. -i index name, -o output directory, and then read1, read2. So -i index name, so that was the Cariha index, -o output directory. So let's call it grain Callisto, and then we go back to the data directory and look at the grain read 1 and data grain read 2 and press enter. Did it incredibly quickly. So that was the Callisto quant for the grain data. And now we do the same for the leaf and the roof. So let's do Callisto quant minus I, Kariha index minus O, leaf, data, leaf, read 1, data, leaf, read 2, exactly the same, and then also Callisto quant minus I, Kariha index minus O, root, and then data, root, read 1, data, root, read 2, and now in this folder, we have grain Callisto, leaf, and root. So if we go for root, then we have 3 files, abundance H5, abundance TSV, and run info JSON. So the H5 file is only machine readable, so it doesn't make any sense to look at it. But if we look at the abundance TSV, this gives the results. So target ID is the gene name, length is the length of the gene, effective length is how many different k-mers are different from other genes, estimated counts is how many reads come to this gene, and then TPM is the value, different expression values normalized. And here we see on the last column that TPM for the first one is 451,000, and then second one is 142,000, and then there's 0, 110, 0, 0, 0, 1,400. So there are already different expression values. And if we go to, say, leaf and look at the abundance TSV, we see different values. So already from these little tables, we see that there are many more genes expressed in the leaf than in the root in this area. And let's see, just for fun, the grain. Grain, abundance, TSV. So the grain is similar to the root. Not every gene is expressed, but leaf has lots of expression, and that's great. So that was how to do Callisto.